One of the things that quantum computing is really good at is modeling the quantum behavior of molecules. So one of the tasks is to come up with a way to create ammonia, which means we're putting nitrogen in a form that the soil can use it as a fertilizer, but do it at room temperature the way nature does. That seems on the surface pretty easy, because all you have to do is take nitrogen, which is 2 atoms of nitrogen. Unfortunately, it has a triple bond, so it's really hard to break that bond. And then all you need to do is turn it into NH3, 1 atom of nitrogen and 3 atoms of hydrogen that will create that triple bond and make it super stable so that it can be used as fertilizer. Right now there are ways to do this, but they are very energy intensive. You have to heat the material up at a very high temperature. You have to put it under pressure, and in the process of doing this, you release, guess what? Our old enemy, CO2 emissions. Nature does that without the high temperature, without the high pressure, and without the CO2 emissions. So if we could use a quantum computer to model this activity, then we would be on the road to some amazing scientific breakthrough. But as I pointed out in the previous video, having hundreds of quantum bits, just even hundreds, in a fault-tolerant format is not available yet. So what am I going to do? Well, I'm not giving up. What I'm doing is I'm going to start with hydrogen, and that's what this video is about. Let's look at hydrogen and see how a quantum computer models hydrogen. Then we're going to go from hydrogen and look at lithium hydride, where lithium has 3 electrons, and then slowly build our way up to nitrogen. Okay, it's difficult for me to talk about hydrogen without drawing a diagram, so here I go with my little pad, and let's see how well we do. Here's a proton, and that proton is a particle. And here's another proton, and it is also a particle. Now, where are we headed? We're headed to look at the molecule hydrogen and model the hydrogen molecule and come up with some of its properties with the quantum computer, and then we're going to compare that to what the actual properties are that are measured without a quantum computer. Now I'm going to switch colors, and I'm going to boot the electron, but I'm going to do the electron a little bit different than normally done. And what I'm going to do with the electron is just draw a circle. It's a pretty lousy circle, but there's a circle. And this other proton has another circle around it, and you notice I didn't put a little blob there, because I don't want you to get the idea that the electron has any definite position, because it's more of a wave particle. Even the proton, according to quantum mechanics, has some wave properties as well, but it's much more of a particle than an electron. But anyway, there's the 2 electron clouds. Those electron clouds, why are they around the proton? Well, the electron clouds carry a negative charge, and the red dot in the middle, the proton, has an opposite and equal charge. Nature's kind of neat that way. So what we can say is that there's a certain energy associated with this electron. And if the proton's moving, it has some kinetic energy also, but mainly the energy is from this electron. And I'm going to say that this electron has a 1s orbital. And this one has it's the same atom, so it has a 1s orbital also. Now, if we look at this, let's try to figure out what the energy would be. Well, the energy of this electron matches this electron, but what's going to make that electron change energy? Well, if a photon came in here and banged against the electron cloud, then that might advance it out into another energy level. And that energy level we can account for, and we actually have to consider when we're talking about quantum computing. But anyway, that left to its own devices, out there floating in the wind, which there's always something else around there that's going to affect it. But if we just consider these things in isolation, that's what everything's going to look like. Now, what happens if the two atoms come close together? What happens if they start approaching each other and start getting closer together? I'll just draw an arrow here, and to show that it's nothing special about that one atom, I'm going to put another arrow here. So they're starting to come together. Now, why would that be? Got two negative charged clouds, wouldn't they repel one another? Well, yes and no. If they get close enough, this electron cloud is kind of attracted towards this proton, and this electron cloud is kind of attracted to this proton. So if they get really close enough together, darn it, I've got to redraw this. So if they get close enough together, we can draw a picture kind of like this. And here's the proton, and here's the proton. And what I want to show is these two electrons are kind of sharing. This one electron isn't necessarily associated with this proton only, and this electron cloud isn't associated with this proton only. So at this point, what are the energies of these two electron clouds? It turns out that the energy of each of these are actually higher energy than if both of these are combined. So it's like they achieve a new level when they're attracted by two protons rather than one proton. So these really are a single shared energy level. And this energy level can only accommodate electrons with a certain kind of spin. Or I should say only one kind of spin is allowed. This spin of plus 1/2 or spin of minus 1/2. Now, what do we call this level? Do we call it a 1s, or what do we call it? We call this new orbit a sigma 1s. And this sigma 1s can accommodate two electrons. Now, just for completeness, there's also something called a sigma asterisk 1s. So, and what is this? This is when now remember, these are really overlapping orbitals. 1s orbitals start overlapping, and if they overlap, they can be constructive interference, which is one kind of energy level, which is lower, or there's a higher energy level called a sigma star, which is when they're out of phase. And so this is a little bit harder to fill. It can be filled, but only if we fill these first. These are going to be the ones that are going to be filled first. What causes these things to want to join? Well, if it's a lower energy level, things go from higher energy to lower energy level, lower potential energy. So this actually takes some effort to break these back into two again. And that effort to break them in two again is called bonding energy. The bonding energy is the energy that you have to put into it to break these two apart. Now, hopefully this is enough information for us to get into the quantum computing part of it. If you want some numbers to go along with this, the single hydrogen energy is 13.6 electron volts, which if you're used to atomic stuff, then that will make some sense to you, or physics stuff, definitely, for electron volts. And the energy for two joined together, that's what we're trying to find out with the quantum computer. But I did a couple videos about a year ago that had to do with finding the numbers and doing the math. So if you like that stuff and want to dive into it, I added those two to that. One was the radial energy, and one was the eigenvalue functions for the radial energy. So it goes through all that stuff and shows that elemental 13.6 electron volts that goes along with that. But next, I'm going to show a Python program, which is the easiest way to get into programming a quantum computer to simulate molecules, and we'll go from there. Did you forget what we were doing? What playlist is this? Physics 101? No, it's quantum computing. And I just happened to pick up this molecular stuff because that seems to be one of those things at the breaking edge of what's going on today. This trying to get ammonia fertilizer out of low energy chemistry. So what's behind me? What's behind me? I think you can see. See my little cursor? See this little stuff up here? This looks like a computer terminal. Let's reduce the size of my window so that we can see what's going on. Here I go. I'm shrinking, I'm shrinking, I'm shrinking. And what is on there? Well, this is a prompt, and you can see something about my login information, my home directory, and Qiskit project, which is that's the software, that's the magic software that does all this stuff. And you can hook to an IBM computer, but I'm not going to do that. I'm just going to do simulation. So let's go ahead and get started with this. I'll look over here at my terminal and let's see what we can come up with. Well, you got to use an editor to look at a computer. So let's go ahead and look at an editor, and the editor I'm using is Nano. Anyway, let's get started, and I'm going to type in, well, let's just see if I've got that command in there. Oh, there's my command. Nano H_HE energies. Now wait a minute, I don't see hydrogen molecule there. I know because as I started to look into this, the hydrogen molecule is much more complicated. So I've already done the manual calculations of hydrogen in another video, and why would I step up to helium next? Well, helium's the next step, and it can't be solved exactly. It has two electrons. You've got one nuclei, that's one body, one piece of the pie, and two electrons. So if you have two electrons, that creates a three-body problem. Have you ever heard the three-body problem is you can't solve it exactly because they're all interacting with one another? Well, that's what's going on. So we can do the hydrogen and solve it exactly, just like we do on pen and paper, like I did in that one video, which was probably pretty boring if you didn't like that stuff. But anyway, I'm going to show what this thing looks like. Well, okay, quit talking and let's see something behind what you're talking about. Okay, let me scroll up here a little bit. Or no, I don't have to scroll up. That's the very top of it. Okay, if you look at this, it says hydrogen and helium ground state energy. Here's the Qiskit. This is the version number 1.4.1. And then there's nature, which is the stuff that does physics stuff. That's nature. Physics stuff is nature. Okay, 0.7.2 compatible. The hydrogen is solved exactly in a manual 1-qubit Hamiltonian. Whoa. There's a lot of stuff going on under the hood. Let's see how long this program is. Well, let's see. Whoa, that's a short program, isn't it? And the output is these energies. So why doesn't Mr. Wells just shut up and run the program and let's see what it looks like? Okay, let me get over here. I'll do a Control X and that exit it out. Then I'm going to hit this key a few more times and oh, there's the Python command. And the Python command is in a very special environment called this Qiskit. Notice that's in front of the normal prompt. Those of you that are Unix geeks, this will set up an environment where I can use a lower version of Python without messing up my normal Python stuff. Anyway, let's go ahead and run the program and see what happens. Okay, took some time, did some grinding on stuff, who knows what happens. And this little thing at the top might worry you. It says deprecation warning. That just means that some of my stuff is a little out of date. And one of the things you'll find when you get into Qiskit programming, you'll notice that it has version lockup. It takes you all kinds of time to resolve the versioning to get everything to work. Now let's see what's coming on here. Here's hydrogen, and the energy was 13.6 electron volts. That's exactly what we got before. And we have helium, which is, what I want to point out is, look how much larger this number is. That means to break those 2 electrons free from helium, atomic number 2, 2 electrons, that takes a lot more energy. I don't know what 13.6 and 76 is, but let's see, 26, anyway, it's, what is it, 6 times more? Yeah, that's 6 times more energy to get the helium things out. Now, does that make sense in nature? Well, is hydrogen stable by itself? No, it wants to form a hydrogen molecule. So the hydrogen atom isn't by itself very much unless you ionize it or do some little tricky stuff. But the helium atom is very stable. Does helium combine with other stuff? No, it doesn't. It's completely stable because to break those electrons free, to do reaction stuff, it's not going to happen. Now, I could go through and explain this program in detail, but I think this is enough for now because I actually showed you that I could do quantum computing.